caused problems when it was on an exam. What we have are 3 children, and they're standing on a frictionless pond of ice. And they're wondering, how are we ever going to get off of this pond? Because when we try, we just fall down. And then they decide to put their hands together and push. And this is what it looks like beforehand. And afterwards, after the push, this child is going at 4 meters per second. And this child is going at 5 meters per second. And we're asked what happened to this child here. And what we want is the direction and the speed. Now the first part of this question asks, which is bigger? The impulse on child 1 or the impulse on child 2? And this turned out to be a problem because I had way too many students in the class answer it as, Greg, you can't fool us. You taught us that in any collision, and an explosion is a collision, the impulse is 0. So it's 0 for student 1, 0 for student 2, 0. Well, that's what they got, was 0 points. That was the part that was 0. I told you that for a collision, and an explosion is a collision, that you could take this equation and you could be sure that the impulse was going to be 0. And that would take you straight to this equation. But there was a condition. The condition was you had to include everything in your system that collided or exploded. So this is for the system, and for the system. And that's what got us to this formula, where the system momentum was conserved in any collision. However, if I'm only looking at child 1, her momentum's not conserved, and that means that she experienced an impulse. So if I just look at child 1 and use the general momentum plus impulse is equal to final momentum. Initially, she's just standing there. She has 0 momentum. And then an impulse acts on child 1. And afterwards, she's moving north. Now, we're told that the mass of child 1 is 50 kilograms. And after she pushes the other 2, she's headed at 4 meters per second north. So this is going to be 50 kilograms times 4 meters per second north, or 200 franci north. Now if I do the same thing for child 2, she starts with 0 momentum, and then there's an impulse on child 2, and after the impulse, she has a mass of 30 kilograms. After she pushes, she's going 5 meters per second, so that's going to be 30 kilograms times 5 meters per second east, or 150 franci east. Now this is the magnitude, and that's what we were asked to compare. The magnitude of the impulse on child 1 is bigger than the magnitude of the impulse on child 2. because 200 is bigger than 150. Now, let's get to the meat of the problem. When this was an exam question, the most common wrong answer was to say, hey, initially they had no velocity, and so afterwards, this velocity has to cancel out those velocities. So if I look at this velocity by 3, it's got to have an x part that cancels out the 5, and it's got to have a y part that cancels out the 4. And so this is going to be 5 squared plus 4 squared square root. Tell your neighbor why that's not only wrong, but sick and wrong. Very, very sick and wrong. The sickest of wrong. This is Ebola wrong. It's way sick. What you should have said to your neighbor is, there is no law for conservation of velocity. Velocity is not conserved in a collision. Momentum is conserved in a collision. So I've got to go back and start over. Initially, the 3 children are just standing there. That gives me a momentum for the system of 0. That means that after the explosion, after they push apart, it still has to add up to 0. Well, here we have 200 franci going north. Here we have 150 franci going east. And that means that the momentum of this child, P3, which is the mass of child 3 times her velocity, that has to cancel out this momentum. And so that means that the x part of child 3 momentum is 150 franci west, and the y part is going to be 200 franci south. Now, I recognize this is a 3, 4, 5 triangle, so that makes this 250 franci, and it makes this 53 degrees. It's a 3, 4, 5 triangle. And so I would say that the momentum of child 3 is 250 franci at 53 degrees south of west. Now, we weren't asked for the final momentum of child 3, but her velocity. Since this is her mass times her velocity, we can solve for her velocity. Her mass is, the mass of child 3, we're told, is 50 kilograms. And so this is going to be 250 over 50, or 5 meters per second at 53 degrees south of west. Check that your neighbor got that right.
I did.
Now, I just want to point out, before we go on with today's lecture, that as people came into my office hours today, I saw a lot of people with wrong answers to problem 8. We had 3 cars, each of 2,000 kilograms, and each going 30 meters per second. Now, the momentum is going to be mass times velocity, or 60,000 franci. Now, here's the mistake everyone was making. They said, well, if this car's got 60,000, and this car's got 60,000, and this car's got 60,000, That's 180,000. Well, that would be true if we were talking about money or energy, but momentum's a vector. And so, if I just had those two cars, the momentum of the system would be 0. And what people were missing was this table. I told you, you always, in a two-dimensional problem, you always need to separate out the x part from the y part. If you had done that, if this was car 1, car 2, car 3, car 1 would have momentum all in the positive x direction and nothing in the y. Car 2 would have momentum all in the negative x direction and none in the y. Car 3 would have momentum all in the positive y direction and none in the x. And now if I add these up, this cancels that and I get nothing in the x, I get 60,000 in the y. Now that's going to change all of your answers all the way through the problem. So don't make that mistake when you get to the exam Thursday night. Questions on either of those problems? E is?
E for number 8.
What was part E? I don't have my book.
Change in x at what bar?
Oh, well, anytime you're looking for a change in x, that's energy problem, okay? So what I would do is I would take those 3 cars, mangle, and I would first of all find out how fast they're going right after the collision. And I do that by using the fact that the P final for the system is equal to M total times V final. So if this is 60,000 franci, and I've got 600 kilograms, 6,000 kilograms, then my V final is going to be 10 meters per second. Is that right? Well now, if I use the fact that it is losing energy because of negative Verk, I start with this equation. If it's on a level road, there's no gravitational energy, there's no springs, so this energy is 1/2 mv initial squared. It comes to a halt having energy of 0, and it does that because the friction force does negative Verk on it, force times distance. So I know that this is 6,000 kilograms. This is 10 meters per second, and I can find the friction force because I'm given the coefficient of kinetic friction, so I can find the distance. Okay. New topic. This is the last topic before the exam. There will be no new topics after this. If I were to tell you that Greg can do 5 billion joules of Verk, and then I asked you the question, is Greg a powerful man? And be careful how you answer that, because there's an exam coming up. There's a question that you're going to want to ask. And that is, can Greg do all that work in a minute, or is it going to take the rest of his lifetime, like 4 years, to do that amount of Verk? Okay? So that gives you an idea of what we mean by power. Power is how quickly you do Verk. How much Verk you can do in 1 unit of time. And the unit that we take is typically the second. How much Verk we can do in 1 second. Now, I can write that this way. You take the total amount of Verts, you divide by the total number of seconds, and that gives you power. You can see the interpretation by setting delta T equal to 1 second. If this is 1, then the power is the Vert. The Vert that you can do in 1 second. Now, Vert is what changes energy. So another way of thinking about power is how much you can change the energy of something, or how much energy you can deliver to something in 1 second. Now, there are a lot of problems in which you push with a constant push and you get a constant speed. Now, of course, that's because as you're pushing with 50 newtons this way, the friction force is pushing with 50 newtons the other way. But if I just want to know how much power I'm delivering, I don't care about the friction, just how much power I'm delivering, and this is a very common situation, I can rewrite this as force times distance and separate out the distance and put it over the time. Now, the distance over the time is the speed. So in the special case where you're pushing with a force that always stays the same and your speed is always the same, then you can describe the power delivered by the force times the speed. And you're going to need that in 2 of your homework problems for Wednesday. Now, what are the units of power? Anyone know? What? What? Yeah. A watt. A watt. Okay, again, named after a famous professor. You know, that's the way we honor dead professors. We name something like the Francis after them. Okay, and it's a joule per second. Now, by show of hands, how many of you pay your own power bill? Okay? So, when you pay your power bill to the power company, what is it that you're buying from the power company? What do you pay for and actually get from the power company? What is it you're buying? Kilowatt hours. Kilowatt hours. And the question is, what is that? Well, a kilowatt is 1,000 joules per second, 1,000 watts, and an hour is 3,600 seconds. It seems a little longer in a physics class, but that's all it is, 3,600 seconds. If I multiply those out, I get 1,000 joules per second times 3,600 seconds. The seconds cancel, and I get 3.6 million joules. When we call it the power company, it's a misnomer. We're not buying power from the power company. We're buying energy. It should be called the energy company. Now, this is the amount of energy that you would pay 12 cents for. And that amount of energy would take a 100-watt bulb and light it for 10 hours. Okay? So that's a pretty good deal. Now, when we're talking about electric energy, and this is 207 stuff, this won't be on the exam, but a lot of people think that what you're also buying are electrons. That they're sending electrons through the wires to make your lamp light up. Well, you remember that the power at the wall here is alternating current, meaning that they turn the battery around 120 times per second. It's 60 hertz. They essentially change the polarity of the voltage 120 times each second. So that means if you look at an electron that's going through the filament of your lamp, that electron, let's call him Fred, he's going through the filament, and then they change direction on it, and he's got to go the other way, and then he's got to go the other way. And they change that direction 120 times per second. Now, when I was growing up, I used to think that those electrons were going through the wires at the speed of light. And I used to think, whoa, how do they make the corners? How do they make the turns? Well, it turns out that they are moving incredibly slowly. if we take that electron and paint him green, call him Fred, and we look at him as he goes through the starting motor of your car, from the negative terminal of the battery through the starter and back to the positive, if you leave the key turned in the ignition for 2 weeks, that will give Fred enough time to make it through the starter and back, moving incredibly slowly. So that means that when the power company lights up your lamp, what they're really doing is going in to the electrons that were already in the filament of your lamp. You didn't buy it from the power company. They came from the goodwill. Okay? And they're taking those electrons and they're just shaking them. Okay? Just back and forth, back and forth. That's what causes the filament to heat up and glow. Okay? Now, many years ago, I used to work at Lawrence Livermore National Laboratories. That's this nation's, well, it's the nuclear weapons lab for this nation. I never worked on nuclear weapons, but everyone else at the lab says that too. Anyway, at that weapons lab, we had the most powerful laser in the world. To this day, it's still the most powerful laser in the world. It's called the Nova laser. And it's made up of 10 laser beams. And the beams are in a great big room the size of a football field. I mean, this thing is enormous. This is a scientist. They're a little smaller than humans, but you get the drift. This thing is huge. And as the laser beam goes down these 10 beam lines, they pass through these great big neodymium lenses. Now, before the laser goes through the lens is excited with energy, and to a higher energy state if you've taken your chemistry class. The laser beam going through this lens causes all of the excited atoms to fall down to their ground state, each atom giving off another photon and making the beam stronger and stronger and stronger. And then they take the 10 beams and they focus it down on a target. And again, these are scientists here, so you can see the scale. And they focus those beams down so small that they can hit this target right here. A little tiny bead of glass filled with a little bit of deuterium and tritium. Now, by hitting that on all sides, 10 sides, with these massive laser beams, they create the same temperature and pressure in the target as is in the center of the sun. And that causes the same reaction that we have in the center of the sun, fusion. And by taking those small elements, deuterium and tritium, and fusing them together, a huge amount of energy is released. How much energy? If you take a gallon of water, seawater, and you remove the heavy hydrogen, the deuterium and tritium, you've got 99.999% of your water left. You can still surf, okay? You take that tiny amount of deuterium and tritium from 1 gallon of seawater, you fuse it, and you get enough energy to equal 600 barrels of oil. If we get this to work, it's free energy for everyone. Free energy for everyone. Now this laser, the reason I'm telling you this, is that this laser delivers 200 times the total power output of all the power stations in the United States. All of them combined. 200 times that. Makes you wonder, where do they get this power? Canada? Mexico? No, they get it from Pacific Gas and Electric. And this power is trickled all day long into a great big room filled with capacitors that stores the energy. Now, when I look at the formula for power, it's the energy that you deliver divided by the time. There's two ways to make this ginormous. One is you could deliver an enormous amount of energy. But that's not the way they do it. They do it by delivering the energy in less than a billionth of a second. If I make this time really, really small, my power gets really, really big. The catch is, they only deliver that energy for a billionth of a second, and then they've got to store energy all day long for tomorrow's run. Whereas the energy that's coming from your power stations, they got to deliver it to your house all day long. Okay, so it's a little misleading when we say 200 times the power output of all the power stations in the U.S. Now, every now and again, if you read the newspaper, you'll see some of our politicians griping about the number of state employees we have in Montana. They'll say, Montana has more state employees per capita than any other state in the Union. The key is the per capita. We don't have any people in Montana. Okay, we got one governor. California has one governor. That means like we've got 800 times more governor per person than California does. Okay. On the bright side, we got fewer state employees per cow than any other state in the Union. It's all in the division. It's all in the division. Okay? Now, there won't be anything about fusion on the exam. But as you go through life, it's something you should know about. When I started working on fusion many, many years ago, that would have been 30 years ago, we were telling our parents that we were 20 years away from solving this problem. When I talk to my friends now who are still in the field, we are only 20 years away from solving this problem. So we're just on the cusp. Just on the cusp. Now, there's what it looks like when we're bombarding the target. And there's a great big huge bay of capacitors. We'll learn about those in 207 when you take that class. Okay. For the rest of the time, what we're going to do is use the principles that we've learned thus far in our physics class to try to calculate the muzzle velocity of a gun in as many different ways as possible. Now, today, the only kind of gun that I can possibly bring into class is this one here. Okay. There's some bills before the legislature that if passed, every single one of you will be packing, which makes me a little nervous at exam time. Anyway, if you wanted to calculate how fast the bullet was traveling when it left that barrel, how many different ways could you do that? Be creative. Talk to your neighbor. Come up with at least 4 or 5 different ways. I have to apologize. We actually were scheduled to have a lot more different demos today. But over the weekend, Jerry, who does our demos, was mountain climbing by himself and fell 30 feet and landed on a sharp rock. And so this morning, when I was expecting everything to be set up, next thing I know, Jerry crawls in on crutches, barely moving. Oh dear, oh dear. So he's not doing so good. I've come to appreciate just how important it is to have people that help to, set things up. So anytime you see Jerry, just thank him for all the work he does to make our class move so smoothly. What did we come up with? What ideas did you have for measuring this muzzle velocity? Raise your hands, because I'm still waiting for my hearing aids to come back from Costco.
Force times changing distance.
Okay, force times
The changing distance.
the change in distance. Okay, so if I could compute the force exerted by the black powder or the explosion and the distance of the gun barrel, that would work. Other ideas?
Using energy, the chemical potential energy of the explosive plus the gravitational potential of the ball.
Okay.
Altogether.
So now the part about the chemical potential energy worries me a little bit, because we can dance when I know about chemical potential energy on the head of a pin. But you're right, if we had a formula for that, we could do it that way. What about things that we learned in this class that we've studied this semester?
Just do the time it takes from when you pull the trigger, when you fire and hits until it leaves the barrel. That's a delta X.
Okay, so if we now if we take that delta X as it's in the barrel and divide by the delta T, that's just going to give us an average.
Yeah.
And then what do we have to do to the average velocity to find the final velocity? Multiply by 2. Yeah, if we start from 0, the final has to be twice as big as the average. Yeah, so that would work. If we could measure that little bit of time that it was in the barrel. What if we wait till it gets out of the barrel?
Fixed delta X and the time it takes between the two.
Exactly. So we know that if we fire it horizontally, the horizontal velocity doesn't change if we ignore air resistance. The vertical velocity changes by 9.8 meters per second every second, but not the horizontal. So if we take that distance and divide by time, what else could we do?
Wait for it to hit something?
What's that?
Wait for it to just hit something?
Yes, we could have a collision with this. We just studied collisions. We could fire this into a block of wood and see how much it moves that wood. And that's the way they actually do it at FBI headquarters. What else would
You could put on a frictionless surface and look at the mass of the gun and the velocity afterwards.
Wonderful. Okay, if we have the standard frictionless surface, we just look at the recoil of the gun, and we conserve momentum during that explosion. Whatever momentum this has, the gun has one way, the bullet's going to have the other way. Good.
Spring energy, so spring constants.
Okay. In this case, would need a spring constant, but a lot of guns don't have springs, and so with energy, we'd have to go back to the chemical potential energy idea. That would work. Let's summarize some of these ideas that we've come up with. One idea that didn't get mentioned is just to get a motion detector, a little speedometer, as it were. And I think we can get rid of that plan because it looks dangerous. I found this on the internet, and I just want to say some people have worse jobs than yours. Okay, there are some jobs that are just not fun. That's going to leave you worried. So let's talk about the kinematics approach that was presented by this gentleman over here. If we fire the gun horizontally and measure the distance and then divide by the time, we would have the horizontal velocity, which is the original velocity. That's what it left the barrel with. Now, that time is going to be hard to measure because it happens pretty quickly. We could also do it with only a meter stick. And we could do that by measuring the height. Now, if I measure just the height of the bullet when I fire it, and I use my kinematic equations in the y direction, So if I call down the positive y direction, then delta y is equal to v naught y delta t plus 1/2 plus 1/2 ay delta t squared. Well, if I measure that h and I call down the positive y direction, delta y is going to be the h. It starts with no velocity in the y direction, so that term goes away. And what I get is 1/2, if I call down positive, this would be 9.8 meters per second squared, and then delta t squared. And that gives me a delta t of 2h over 9.8 square root. Now, let's try that. Let's actually get a muzzle velocity for this guy. Do I want to measure to the bottom of the bullet, the middle of the bullet, or the top of the bullet from the floor?
Center.
What lands on the floor? The bottom. So I want to measure to the bottom, and that is going to be 107 centimeters. So the H is 1.07 meters. So I come over here and I take 2 times 1.07 divided by 9.8 and then square root. Someone with a calculator, be calculating that while I find the range. Okay, so that's about right. And now we put Osama bin Laden, the guy that George Bush got. Oh wait, it was the other guy. Yeah, now I remember. The guy that gets things done. Okay. Let's see. Oh, that's some kind of aim. 2.6 meters. So L is 2.6 meters. Delta T is, what did we get?
Point 15.
Point what?
15.
I think point
0.15.
0.47.
0.47 sounds right. Okay, did you square root it? Yeah, this sounds right. So that means a velocity of 2.6 meters over 0.47 seconds, or around 6 meters per second. Now, if you're working for FBI and you want to measure or calculate this muzzle velocity for a gun that was used in a crime, you don't want to go outside and fire it horizontally. That's going to cause problems. So what you do instead is you lean out the window of your building if you're in a high-rise. Oh, that's how you do it. And you fire the bullet straight up. And you have your colleagues on the upper floors kind of peek out the window, don't lean out too much, and see how high it goes. Okay? Now, if I take this gun and I put it here, who's got the bullet? Thank you. So now I fire it straight up, and if I know how high it goes, I can use energy conservation. At the bottom, when it leaves the barrel, if I call that height 0, it's got kinetic energy. When it stops at the top to turn around, it no longer has kinetic energy, it just has gravitational potential energy. If we ignore air resistance, then what we have is the kinetic energy leaving the barrel is equal to the potential energy at the top. We solve, if we know what H is, we solve for V. Okay? Now, if we had time to do that, what we would get is something very, very close to 6 meters per second. Now, again, most FBI agents are kind of hesitant to lean out their window and fire a gun straight up. Again, there's consequences. So instead, they do what we talked about, where you fire into an object, like a block of wood, and you watch as that block of wood gets pushed across a rough surface. Now, if you measure how far it goes, and you're able to measure the friction force by using a force probe and pulling that block along the surface at constant speed, you can solve for the muzzle velocity. First of all, during the collision, do you conserve momentum or energy? Momentum. It's a maximally inelastic collision. They stick together and move together. So energy is not conserved. It's momentum that's conserved. And here, I'm going to have, before the collision, it's just the bullet that has momentum. And remember, that's what I'm looking for, that muzzle velocity V. After the collision, the block and the bullet stuck together are moving at some final velocity V block. If I know what V block is, and I know how massive the block and the bullet are, I can solve for V. Well, how do I know how fast it's going after the collision? Well, I measure how much Verk is done, and I let that Verk steal the energy. Okay? So I look at the kinetic energy that the block has with the bullet embedded in it right after the collision. And then I look as friction takes that energy and whittles it down to 0 over a distance of delta x. If I solve that for V block and then put it into the other equation, I can solve for the muzzle velocity. Now, what's more common is for them to fire into what's called a ballistic pendulum. And in that case, you fire the bullet, and that causes the pendulum to swing, and eventually it turns around to come back down. Now, the height at which it turns around allows you to calculate how fast it was going right after the collision. So again, if you use momentum conservation, you can find the speed of the bullet. Now, we actually had setups for these things, but as I say, I apologize that we didn't get to do that. On Wednesday, I am going to just practice to get you ready for the exam. And on Friday, we're just going to go over your graded exam. That's an optional day for you. You can come or not come. Okay, we'll see you on Wednesday, people.
Great.